Hi, welcome to this lab module. In this lab module, we will be talking about fabricated sensor on silicon substrate with gold deposition, interdigital electrodes and micro heaters. So, how can we fabricate the material on a silicon substrate? Now, I told you substrate does not confine to only silicon, substrate can be glass, substrate can be polymer. In principle, substrate can be any material on which you are growing a device or you are fabricating a device, alright. So, if I talk about silicon as a substrate and I talk about gold depositions, interdigital electrodes and micro heater, then what I am talking about? First you have to deposit a metal and metal would be nichrome or platinum. So, if you see the screen, what we are talking about is if you take an silicon wafer. Now, all of you are kind of expert in understanding the process flow. So, I am not going in detail of the process flow, but if you have silicon wafer and if you oxidize this silicon wafer, right, then this is called oxidized silicon wafer. This oxidation can be done using thermal oxidation, right, SiO2, this is silicon. Now, on this you need to form a heater. So, how can you form the heater? You can form heater by depositing a metal and then performing lithography. So, if I deposit a metal and perform lithography, I will have my heater material as shown in figure, and this one would be, let us say, platinum, alright. Now, on this how can I have interdigital electrodes? So, if I directly deposit interdigital electrodes or fabricate interdigitated electrodes, IDEs, right, you know IDEs looks like this, finger electrodes, like this. So, if I want to deposit and fabricate IDEs, right, how can I use that? And these IDEs are made up of gold, right. We always say chrome gold because chrome would be helping in the addition of gold. So, if I deposit metal on metal, it will short. So, I have to deposit an insulating material and then perform lithography to open the window. Window is only for contact pads here, right, contact pads. Now, on this if I deposit a metal which is my chrome gold, right, if I deposit a metal which is chrome gold and I pattern it, then I will have my interdigitated electrodes, right. Why I am depositing metal on metal here? Because this is a contact pads, thicker the contact pad better it is because it will have a ohmic contact versus rectifying contact. So, how to create this kind of platform or how to create this kind of device, this is what will be taught or will be shown to you in the lab class, and I will request my teaching assistant Anil to show it to you this particular lab component of this subject. So, till then you take care and I will request Anil you please take it over.
Welcome. So, what we are doing from past few small modules is that we are trying to see actually fabricated sensors and how they are working, what is the rationale behind the design that has been employed for them and such things, okay. And now last two modules you have seen devices that were fabricated on glass substrate, correct, and you have seen microfluidic channel based devices and you have seen micro heaters and microfluidics combined. So, such devices you have seen. Now, we will see few devices that are being fabricated on silicon wafers, okay. Majority of the devices would be on silicon wafer and a few microfluidic devices are mainly done on glass wafers, okay, generally. Now, as I told you, before you make any device, you have to clean the wafer, as professor would have told you, you clean the wafer, then you deposit a specific material, especially sensing materials like electrical sensors. Mostly we use some metal, like you might use platinum, you might use gold, you might use aluminum. So, different you might use nickel, you might use nichrome for micro heater. So, many different types of metals may be deposited on silicon wafer. So, to start off, I will show you a silicon wafer where a blanket deposition of gold has been done. So, this is a silicon wafer with gold deposited on it. You can see how smooth the surface is. You can see the amount of reflection from it. You can see the gold. I can see the gold reflecting on the camera itself and creating light. The light falling from the top is reflecting from the gold and going onto the camera. So this is gold deposited, blanket deposited gold on silicon wafer. The silicon wafer's thickness is, so if I come to the parameters of deposition, so this has been deposited, so such gold material can be deposited using either sputtering method or E-beam evaporation method. Okay. So in sputtering, as you know, there will be a target and the gold will be, like it's a very active process where actively the gold atoms will be bombarded by argon atoms and the gold atoms will be taken out from the target and they will be deposited onto the substrate. This is our substrate. That is sputtering. And another method of depositing gold is E-beam evaporation, which is a more tender method where electron beams do the process in a vacuum environment and deposit gold. Okay, so this has been deposited using E-beam evaporation. Now, how much thickness of gold is there? So this has actually 195 nanometer of gold, and below that 195 nanometer of gold you have 25 nanometer of chrome. Why is chrome used? Chrome is used for better, so gold by default has very less addition or stiction or attachment to the silicon substrate. So to improve the addition, so you might have learnt this in the theory classes, so we are just showing it to you. So to improve this addition of gold onto the silicon substrate, we use a 25 nanometer layer of chrome. So first we take the silicon wafer, then we will deposit 25 nanometer of chrome, and then we will deposit 195 nanometer of gold. Now people even deposit higher thicknesses of gold. They can go up to 400 nanometer, 500 nanometer. But when you do that, what you have to take into account is that as you increase the thickness of gold that you deposit on silicon, the stiction, the addition of that gold layers will be reducing as and when the thickness goes up, because the effect of chrome's pull on gold will be lesser as the thickness goes up. On top of that, material cost is something else that you should be worried about. So we have done this deposition using a central facility in the campus in IISc. There are constraints that if you are depositing gold or platinum or such precious metals, you cannot cross 200 nanometers. You cannot deposit more than 200 nanometers because you are paying a definite amount for the material, right? If you just deposit 500 nanometer of gold, it's a lot of material and it's expensive. So they have put this rule. So that is the process constraint. So whenever in life, or especially in engineering and technology, you will always have process constraints. Like you are trying to make a system. This is a course in sensors and actuators, right? Making a sensor or an actuator is one part, but for that sensor or actuator to be useful to a real world scenario, it has to be packaged into a system, correct? Now you are trying to make a system. Let's say you are integrating the sensor into a system and you have packaging in that, and you are making metal parts for doing that. Now metal machining you will do from outside. Let's say you have found 3-4 vendors who do specific machining and you want specific feature size on that metal. Now your process, your design will be defined by the minimum feature size that the vendor can provide for you. Accordingly, so before you design only, because there is no point in doing a wonderful design of extremely nice features which you cannot fabricate. So first thing that you have to do is be practical, and especially when you are into product development, be practical, and you have to make a reasonable judgment or a what do you call that, trade-off. Yeah, you should make a trade-off between your available resources and technologies and the design that you want. So first thing you do is you will have a rough idea of your design in your mind. Then you will go to the vendors that will do it for you. Okay, you ask them like what is the minimum feature sizes, what are the minimum cutting that you can do, what are the minimum dimensions that you can work with. Accordingly, they will give you the parameters that they can work with. Using those parameters, you go ahead and make your design. That's how you do the product development design. Then you do these parts, individual parts, okay, and then you assemble them together, integrated with your sensor to make the product. Likewise, this 200 nanometer constraint on gold is also a process constraint. You are using one equipment, okay, in a central facility and where there are rules. So you have to follow those rules and you make your devices. So you accordingly you tune your device constraints, you tune your resistance calculations if you are making a micro heater accordingly, and then do your design accordingly. So that is the whole point. So we have a gold deposited 4-inch silicon wafer. The wafer thickness is 500 microns or 0.5 mm wafer, and the deposited gold is 195 nanometer of gold. with 25 nanometer of chrome. Okay, this is one silicon wafer. Okay, now next thing what we do is we pattern on this and make our sensors, correct. Now the sensor that I am going to show you, we have fabricated using platinum. I am showing you gold because right now this is available to you, available to us to show it to you. The sensors can be fabricated on gold also. Why we choose different materials is depending on the design constraints again. So gold will have a very good conductivity, platinum will have good conductivity as also you have thermal properties or a thermal coefficient, conduction coefficient that will be different between platinum and gold. So platinum can also be used as a micro heater. Gold doesn't perform that well as a micro heater because gold's conductivity is extremely high that it cannot dissipate heat. The efficiency is more. So people don't use gold as micro heaters, but platinum people use. Nichrome anyway is a very standard material for micro heater. When you are using platinum, you can use platinum for as both a micro heater as well as a electrode structure, IDE structure. That's the advantage of platinum. So when we have a design where there is a micro heater and an electrode structure together integrated into one design, we would prefer to go with platinum. This is how we would prefer to go with platinum. This is how you make material choices in your sensor design. So like what material to use, how many layers of material to be put, all those things, and how much should be the feature size. So feature size again comes from the thickness that you deposit. How? Because resistance so thick, let's say you are designing a micro heater. Okay, so you make a micro heater like this, like a winding structure will be there, you make it. Okay, just I am showing in my hand, just making a winding structure, you make a micro heater. Now how do you design? Your design is that this much resistance should be there in the micro heater. When this much resistance is there, I apply a voltage, this much current will flow through that resistance and there will be I squared R losses. This I squared R losses will be dissipated as heat. So mCp dt. So mCp dt, Cp is the specific heat capacity of the material, m is the mass of the material. So I squared R is equal to mCp dt, okay, roughly. So dt will be the temperature change that you get. So this is how you mathematically formulate your micro heater. Now what is the resistance if you are making a micro heater? Resistance is, as you know, is rho L by A. Rho is the resistivity, L is the length of the material and A is the area of cross section, correct. I am trying to tell you how the thickness that you deposit comes into play. Okay, so resistivity is rho L by A, correct. Now resistivity, resistance is rho L by A, where rho is resistivity. Resistivity of a material is constant, you cannot change it. So your length you define by the winding pattern that you put on the micro heater. Now how does A get affected? A is the cross sectional area, correct. Now if you deposit a higher thickness of the material, your cross sectional area will increase, correct. Rho L by A will increase. That means when A increases, because it's an inverse relationship, because R is equal to rho L by A, when A increases, R reduces. So that means for a given 2D design of the winding structure of your micro heater, I again repeat, for the given 2-dimensional design of the winding structure of your micro heater, if you increase the thickness of the deposited layer of your metal, your resistance comes down. That means for you to attain a particular temperature using your micro heater, it becomes even more difficult that, or you have to apply a even higher voltage to a thicker layer as compared to a thinner layer. So if you want to attain very high temperatures, it's good to have a thinner layer of the material because A will be less. These are the trade-offs. But then if you have a thicker layer of material, if you are looking at an electrode, a thicker layer of material makes sense because resistance, its inherent resistance will be low. If you are looking at an electrode, the electrode should be able to sense the impedance or the resistance of the substance that is on top of it, correct. The electrode should be able to sense the impedance or the resistivity or the resistance of the substance that is on top of it. When you are measuring such a property, the inherent resistance of the electrode itself should be as low as possible, correct. That should be as low as possible. If that is the case, your resistance should be less, correct. Then it makes sense to have a higher area. So rho L by A, if you make it higher A, then resistance will be less. So for electrodes, for interdigitated electrode structures, as you might have seen in the lectures, for IDEs, it is good to have a thicker material. So now you have seen two cases. If you are making a micro heater, you understood that it is good to have a thinner thinner deposited metal layer. If you are making an IDE structure, it is good to have a thicker material layer. Okay, but what if your design or a sensor has both these things? You have an electrode and a microheater in your sensor. I will show you one such sensor that we have made. So in that case, you go a midway, somewhere in between the thickness will be. So it will not be too low, it will not be too high, it will be somewhere in between. That is what we have done with platinum and titanium. So we have made one sensor like that. In next module, I will show you such a sensor. So I think you understood what I have told you right now. We have shown you how a wafer which have been deposited with blanket deposit with metal looks like. What is the design constraint? How much thickness of the metal was deposited? What is the requirement for a stiction layer or an addition layer? What materials will be used? And what is the design approach if you are making a microheater, and how it is different when you are trying to make an interdigitated electrode. Okay, so with these ideas in mind, we will look at a sensor that we have made in our lab where both these structures coexist and how we have designed them. I will show you under the microscope how they look like. Okay, so that we will see in the next module. Thank you.